Section 7.4, to the end of the chapter, is talking about mathematical proof, and really you can think of this as a separate chapter from section 7.1, 2 and 3. We're starting again, this is not really anything to do with polynomial division. Now, mathematical proof is a huge topic, and it is the most important idea in maths. The difference between mathematics and other subjects is that in mathematics we do what we call a logical proof. We base things on proof by deduction. We don't base things on proof with evidence, for example. So in science, we know that when I hold this pen, if I let go of it, it's going to fall down. And I know that that's true because every time you've ever held an object, you let go of it, it falls. Okay? We then come up with a theory of gravity to explain why that happens. But the order in science goes that way. You look for evidence, you see what the evidence tells you, and if there's enough evidence, we can consider that to be a proof. Now that's called that's called empiricism, right? It's empirical evidence. Evidence from your senses is the idea. So you look at things, you observe things, and you use that for your information. In maths, we don't do that. In maths, we start with things that we know. So this little diagram here, we start with things that we know to be true. Now, initially that means starting with what we call axioms, things that we are going to all agree are true, which, to take some of the oldest examples, are things like if I have 2 points, then I can join those 2 points by a straight line, and that straight line will give me the shortest distance between those 2 points. So that is an example of an axiom. It's something completely sort of basic, very, very simple, something that we're not going to argue with, okay? And we consider it simple enough not to be proved. So we start with known facts, and then we show with logical steps what we can prove from those facts. We have to make logical steps, okay? So the idea of mathematical proof is a really important one because it's everything that we know in maths has been proved at some point, and not just proved because we've tested it. So for example, Pythagoras' theorem, we know it's true, not because somebody went and drew 1,000,000 right-angled triangles and measured all the sides and checked it worked. We know Pythagoras' theorem is true because there is an algebraic proof that Pythagoras' theorem is true. There is a proof by logical deduction that Pythagoras' theorem is true. We can show it's true. Now, once you've seen a mathematical proof and you've understood it, it's impossible for anybody to convince you that you're incorrect. Okay. So, for example, if you know that 2 plus 2 is 4, we know that's true because you understand what 2 means, you understand what 4 means, and you understand what plus means. Something I like to do with classes is just take a moment and try and imagine that 2 plus 2 does not equal 4. And actually, you can't do it. You might be thinking of 2 plus 2, imagine 2 objects and another 2 objects and they come together, and then imagine another object arriving. But what you've really done there is 2 plus 2 plus 1. Or maybe you are deciding that the symbol 2 doesn't mean the same thing as we've always taken it to mean. Maybe you're saying, well, 2 now can mean 3 objects, but that's just changing what the symbols mean. Imagine, think about what addition means. Think about what the number 2 means. If you've got 2 things and you add on another 2 things, you have 4 things. There's no way of anybody convincing you different to that. It's actually impossible to imagine that that is not true. So with all mathematical facts, the same thing is the case. If it's been proved by logical deduction from a sound basis, then it is true, and nobody can convince you otherwise. It's not just that it's with the scientific evidence, the evidence is overwhelmingly strong. We don't think anybody could ever produce evidence to convince us that when I let go of this pen it won't fall. It's deeper than that. It's a case of it's impossible for anybody to produce evidence to show us that 2 plus 2 does not equal 4. Okay, so it's really fundamental to the subject of mathematics. Now I'm going to stop talking about the sort of philosophical side of things. We could talk about that for a long time, but I think we're content with just saying, be aware that it's a very important idea in mathematics, and it's one that we normally credit to the Greeks. Okay, so you often hear this idea that the Greek civilization is the one that invented mathematics. That doesn't mean that before the Greeks nobody could count or add up or build buildings because they couldn't do the measurements. What it means is that the Greeks were the people that came up with the idea of proving things through logical deduction, not just having facts to do with numbers that the people thought were true, but actually having to prove them by logical deduction. So that's the first sort of idea. Secondly, when we see the word proof, we use it all over the place. So you have proof in a court of law, you have proof in science. in maths, when we're doing a proof, we've got to be very careful, we've got to be very picky about what conclusions we can draw. So let's let me talk about that for a little bit, and then we'll look at some of the examples. So let's take this sentence, okay? The canteen always has fish and chips on a Friday. Now, if we heard that in real life, we might think you could walk into that canteen, you could see they're serving fish and chips, and you'd say, ah, well, in that case, it must be Friday. So you might take the view that if you see a fish and chips in the canteen, then that would tell you that it was Friday. But that is not a correct deduction from what we've got here, okay? What this says is that this canteen has fish and chips on a Friday. It doesn't say that it only has fish and chips on a Friday and has fish and chips on no other day, okay? So what we can actually, the conclusion that we can actually draw from this is that if it's Friday, then we are having fish and chips, because the canteen always has fish and chips on a Friday, okay? So if it's Friday and you walk into the canteen, you will see fish and chips. If this statement is true, then this statement is true. When you walk into the canteen on a Friday, you will see fish and chips. If you go into the canteen and see fish and chips, you can't draw the conclusion that it is a Friday, okay? Not just logically from this sentence, we can't draw that conclusion. Now, practically, if somebody said to you the canteen has fish and chips on a Friday, you would assume all sorts of other things. You would assume that that means they have fish and chips on a Friday and not on the other days of the week, okay? Otherwise, why would the person be telling you that? Why it doesn't make it a special thing worthy of notice, okay? When we're doing a mathematical proof by deduction, we have to take the statements that we've got and only look at the consequences of those statements exactly, okay? So that's the first thing. We're going to be very, very precise. Now here are a few more examples, and let's talk about what we mean when we say we'll start with facts that we know, we'll take logical steps, and we will have a statement that we know is true. Okay, so if that process is all correct, if we start with facts that are true, if we take logical steps which are correct logical steps, then the statement that we finish with must also be true. So I've got 3 examples here of logical arguments. Okay, now this one is a very traditional one that people give when you're studying logic. It's so traditional that it has Socrates, who, if you don't know, is an ancient Greek philosopher. But the idea is, if we have a fact, all men are mortal, and we have a second fact, Socrates is a man, then the deduction that we can make is that Socrates is mortal, okay? So if we know that's the case, all men are mortal, Socrates is a man, then Socrates is mortal. So we start with these 2 lines. These 2 are our facts. This is a fact, this is a fact. Now, those 2 are both true, or I suppose we could say statements, right? These 2 are statements, and they're both true statements. We haven't made a mistake in our logic, so our deduction is correct. So that is a good argument, okay? There's no mistakes in there. Now, what if I have something like this? Here, I'm starting with 3 facts, and all 3, I'm starting with 3 statements, and all 3 are true. All people are mammals, Socrates is a person, and horses are mammals, okay? So there's nothing wrong with that, but I've made a mistake in the deduction, okay? Socrates is a horse, because if all people are mammals and Socrates is a person, and I'm getting people and mammals and horses sort of mixed up, so I've drawn the deduction that Socrates is a horse. Well, you can see the sort of thing I've tried to do. I've tried to use the same kind of argument as above, but obviously I've made a mistake there, right? So that one is not a good argument. Socrates obviously isn't a horse. The deduction is wrong, not because I started with incorrect statements, but because I made a mistake in the deductive step, right? So known facts or theorems, logical steps, statement of proof. If your logical steps are incorrect, the thing that you get at the end might be incorrect, okay? And then the third example here is if I start with things that I'm thinking of as facts, but they're not actually true in the first place. So here, all men are immortal, Socrates is a man, Socrates is immortal. Well, if this was correct, then this conclusion would be correct, okay? So actually, there's nothing wrong with the deduction here. There's nothing wrong with this as a logical argument. The problem is that that initial statement is wrong, okay? So we can't conclude that this final statement is not true, not because I've made a mistake in my deduction, but because I made a mistake in my starting point. My starting point has to be true. So we have to have the starting point true, we have to have all the steps correct, and then my conclusion must be true, okay? So we've got 3 stages: correct starting points, correct steps, and then we can trust our conclusions. We have to be very picky about what we're doing, and we have to think very carefully, logically about what we're saying. Okay? Now, I will stop the video there. We're up to 10 minutes, so I'll do some examples of the kind that they want in the textbook in the next video.